Okay. Okay. This is the natural language processing class, and today we are going to study the text generation. So here is the lecture outline. Text generation and encoder and decoder, teacher forcing and beam search, and attention mechanism. So we have finished the text classification, which is the input is the text and the output is a category. And the token classification, in the token classification, the input is each token, and we classify each token into categories. And retrieval is to find the relevant document given a query text. So we perform the retrieval to narrow down the data set. So we cannot read all the text with our MRC model, for example. And then we use retrieval method to reduce the number of documents by finding relevant text or document. And now we are going to study text generation. And so far, we only see the RNN model to RNN model for language model, but there are another architecture for language model such as encoder, decoder, attention, and transformer. So we will see later. We will see these topics later. Okay, here is summarization task. So what is the summarization? That is, we summarize the given text into more shorter text. Okay. So there are two approaches to solve the summarization. One is extractive, and the other one is abstractive. So the extractive approach, your summary is only made up of words, phrases, sentences from the original. So we do not generate any new sentence in the extractive approach. So this extractive summarization can be done by text or token classification problem, because we do not need to generate any new tokens or sentences. So we just classify the given tokens into summarization or not. So the text classification, we decide if each sentence is included in the final summary. And for the token classification, we decide if each word and token is included in the final summary. Okay. And the abstractive approach is the summary is entirely paraphrased, hence often approached as a text generation problem. So because there is no such sentences or tokens in the given text, we cannot perform the summarization by using the text or token classification model. In this situation, to generate novel sentences, we have to formulate this as a text generation problem. Okay. 자, 그래서 summarization이라는 NLP의 태스크가 있는데요. 이제 extractive와 abstractive라는 두 가지 관점이 있다. extractive는 기존에 이제 주어진 텍스트에서 정답을 뽑아내는 것입니다. abstractive는 문장을 새로 만들어내는 겁니다. summarization 문장을 새로 만듭니다. So the extractive summarization is much more easy to evaluate. But the abstractive summarization is not easy to evaluate the performance. Because in the extractive approach, there is a ground truth. We can easily make the ground truth for the summarization. But in the abstractive approach, there are lots of different answers. Okay? So that is why it is difficult to evaluate the abstractive summarization method. Okay, so that is why we, in general, we use extractive summarization method. That is more easy, and that is more easy to train and easy to evaluate. So why not using the extractive approach? But sometimes there is no way to use the extractive summarization method. For example, in the machine translation, we cannot perform the extractive summarization method. What is the machine translation? Machine translation, we convert a sentence in a language into the sentence in another language, such as we convert the English sentence to Korean sentence. So in this case, obviously, by definition, we cannot use extractive approach, extractive method for this task. There is no tokens, Korean tokens in the English corpus, right? So this is why we need text generation method. There is no way to serve the machine translation task without text generation method. Okay. Okay, and this machine translation task is very important task in the natural language processing. And now we think that the machine translation is almost served. Of course, it is not quite effective for long sentences, but in a single sentence, sometimes the machine translation is much more good than human. Okay, so it is really, so for 10 years ago, the machine translation is very, very difficult problem. But now, thanks to the deep learning, we can enjoy the machine improved machine translation method. Okay. Okay, here is the text classification versus text generation. 네, 자, 앞에서 그 extractive 메소드를 우리가 쓴다고 했죠. 왜냐? 트레이닝하기도 쉽고, 왜냐? 클래시피케이션이 쉬우니까요. 이밸루에이션도 쉽고. 그래서 우리가 안 쓸 이유가 없다는 거죠. 그렇지만 extractive 메소드를 사용하지 못하는 경우도 있습니다. 그런 경우는 바로 이런 머신 트랜슬레이션 같은 경우입니다. 머신 트랜슬레이션은 이제 우리가 만약에 extractive로 이 문제를 풀어내고자 한다면은 영어로 된 문장에 한국어로 된 단어가 있어야 하는데 당연히 그런 게 있을 리가 없죠. 그렇기 때문에 우리가 이런 문제를 풀기 위해서는 텍스트 제너레이션 메소드를 사용하는 수밖에 없다. 그런 얘기를 했습니다. Okay, so here is the text classification versus text generation. Text classification is a simple maximum likelihood estimation with cross entropy. And this works incredibly well with a few possible small modifications such as tunneling, soft label, etc. So this is the training techniques. Okay. This is less important here because the maximum likelihood estimation with cross entropy is the important part of text classification. And this annealing and soft label can be changed as time goes because that means I want to say that this maximum likelihood estimation is always used for last 10 years, and I believe that this maximum likelihood will be used for the next 10 years. But for the annealing and soft label, this is not. I think this is less not general method. That means in the last year we used annealing, one annealing method, and here in this year we use another more novel annealing method, etc. Okay, that is not important here. And text classification is can be served by using simple MLE with cross entropy. So this is negative low likelihood. Okay. And the text generation, this is a critical problem, is that the probability space of text is very large. The probability space is still finite if we fix the maximum length, but still very large. It is almost impossible to model all possible probability space, right? So that is much more difficult problem than text classification. For example, given vocabulary size of V and fixed length of T, the text space is in the order of O of V to the X, V to the T. Okay, which is very large, almost intractable. So, as a solution, we can try to define maximum likelihood estimation via conditional probabilities, which is also called as Bayes rule. So P of y given x is equal to P of y1 given x multiplied by P of y2 given x comma y1, and okay, so this is the, and so on, and this is the base law. So this is the equivalent, not approximation. They are the same. This is base rule, and this is computing each probability is much more easier than computing the P of y given x. So here, the text generation when t equal 1. So P of y1 given x times step sequence length. And this is basically a three-way classification. A simple approach would be to just use the last hidden state of an STM for the classification. Okay, so when the sequence length is 1, this text generation problem can be reduced to a classification task, which can be solved by using the last hidden state of STM and negative log likelihood with closed entropy. Okay, and now the text generation when t equal 2. Now we have to handling the P of y2 given x comma y1. The first conditional probability can be identical. How about the second conditional probability? That is the question here. And because when the time step is 1, we can easily solve the text generation task as classification, but now when the t is larger than 1, we cannot formulate this problem as a classification task. So we need a generic way to make this work for t which is larger than 1. 자, 여기서 하고자 하는 말은 텍스트 클래시피케이션과 텍스트 제너레이션의 차이였습니다. 그래서 텍스트 클래시피케이션은 문제가 상대적으로 풀기 쉽다. 텍스트 제너레이션은 우리가 감당해야 되는 프로버빌리티 스페이스가 너무나 큽니다. V의 t승만큼. V는 vocabulary size, 그 다음에 t는 랭스입니다. 엄청나게 큽니다. 이거를 우리가 다 모델링을 하기가 너무 어려워요. 그래서 해결책은 그 베이즈 룰을 사용해서 이렇게 이제 식을 전개하면은 원래 p, y 기분 x보다 훨씬 문제가 풀기 쉬워집니다. 일단 t가 1일 때를 보면은 클래시피케이션으로 이제 문제가 바뀐다. t가 1일 때는 그게 어렵다. 그런 얘기였습니다. 자, okay. So here is the traditional method for NLP, machine translation, which is statistical machine translation. This is used before neural machine translation. So this statistical machine translation did not use any okay. So they used the RNN, but it is hard to say this is somewhat deep learning. Okay, so there are lots of rules, and the rules are defined by human, not learned from data. So imagine that how many rules are required for machine translation. Very large number of rules are needed. So in this is called SMT. In this SMT, we need hundreds of thousands source code. And in the 10 years ago, the machine translation team include 10 to the 50 people, and they write the rules for machine translation, which is very, very, very difficult, and also it is not that effective. So maybe you remember that maybe before 2016, if you tried to use the Google Translator, then you realize that it is really not good. Okay, that is based on the statistical machine translation. Okay, but when the encoder-decoder architecture was introduced, many things were changed. This is also called as neural machine translation. NMT. So this is the paper when was introduced in 2014 by Professor Shaw. At this time, he was postdoc, I think. But anyway, this is the first time to use encoder-decoder architecture for machine translation. And this is also called as sequence-to-sequence. So what is the encoder-decoder? There are two RNNs, and one RNN encode the input x1 to xt into one single vector C. And then using the C, this decoder generate the predictions. So the basic idea of this encoder-decoder architecture is that we can summarize all the information of the input text into one single vector. And then another idea of this architecture is that we can recover, we can generate the corresponding text in another language using the given context vector C. Okay. Okay, so use on RNN to encode the input sentence into a summary vector C, which is the last hidden state of the RNN. Nowadays, it turns out that we can use pooling method for more improved performances. But back then, they did not know uh, the pooling method is effective. So this is possible, but they did not know. Okay, so this is very simple idea, but anyway, they did not know. Use another RNN to iteratively decode a list of vectors where each corresponds to each word of the output sequence. Instead of using LSTM, a simplified version of it, GRU, is proposed, but they are very similar. Anyway, this is a very important milestone of natural language processing, which is almost the first work of the possibility of deep learning in natural language processing field. Okay. So anyway, this encoder decoder architecture is very simple and intuitive, and maybe you cannot understand why people did not uh, use this architecture before 2014, because this is really simple, but they did not know. Okay, so this is the research. Someone invented it, then it looks very easy and simple, and but the first but invention of the idea is really hard. 자, 그래서 인코더 디코더 구조가 이 SMT를 이제 대체하였다라는 뜻입니다. 이것을 우리가 NMT라고 부릅니다. SMT랑 다르다는 의미에서 이제 뉴럴 머신 트랜슬레이션이라고 얘기를 하고요. 이 문제를 인코더 디코더 구조로 풀었습니다. 인코더는 인풋 시퀀스를 전부 서머리 벡터 C로 인코딩을 시켜주고, 그 다음에 이것을 가지고 Y1부터 Y2, YT까지 디코딩을 하는 거죠. 그렇게 하면 우리가 제너레이션 할 수 있다. 그리고 이 논문에서는 GRU를 썼습니다. LSTM을 쓴 게 아닙니다. 그렇지만 그 두 개가 거의 유사합니다. 오케이. So here is the function f. And the input of this function f is h of t minus 1, which is a hidden state, the previous hidden state. And y t minus 1 is the previous output, okay? And c. So in the RNN, there is no c, and there is x, the input of the current time step, right? But here, c is used, and the previous output and the previous hidden state is used. So for generate the current y, current output given the previous output and the C context not summary vector C can be computed using this HT and the previous Y and C. Okay. In this way, we can borrow this probability space. Okay. Now this is GRU, gated recurrent unit, which is very similar to LSTM. But it is worth to see the details of GRU. Okay. Compared to the LSTM, there are only 2 gates. In the LSTM, there are 3 gates, right? LSTM. Input gate, output gate, forget gate, right? But GRU, I don't know the full name of this, but Z gate and R gate. And this ZT and RT can be computed using the linear transformation of the current X and the linear transformation of the previous hidden state and the bias. So this is really the same with the LSTM. In the LSTM, we also compute the linear transformation like this. And here is the expression function. And similarly, we can compute the R gate. Okay. And now the H hat is can be computed by the linear transformation of the current input, and then RT is used as a gate here and for the previous hidden state, and it is linearly transformed. And here is the bias. So this is the difference part from the LSTM because there is no such computation in the LSTM. And finally, the hidden state can be computed by a weighted sum between the previous hidden state and the H hat, and each weight is the Z gate, value of the Z gate. So this is the GRU, and you can think that this is very similar to the LSTM, but more simple. Okay. So many people use GRU instead of LSTM, but still LSTM is also used, also generally used after this GRU paper. So, and the important thing is that they are not used in general in the natural language processing field nowadays. LSTM is sometimes used for speech recognition task, but in the natural language processing, we do not use LSTM or GRU anymore. 오케이. 자, 인코더 디코더. 시퀀스 투 시퀀스가 2014년에 나왔고요. 이거 아까 얘기했던 것 같은데 아무튼 네, 그 중요한 건 이 C가 사용된다라는 거겠죠. 이전에 히든 스테이트 그리고 C가 사용돼서 HT가 계산되고 이게 결과적으로 우리가 앞에서 봤던 이 PY 기분 X를 베이스 룰로 분해한 요 각 텀을 계산할 때 우리가 쓸 수 있다. 바로 그게 인코더 디코더 구조의 핵심 아이디어입니다. 그리고 이게 GRU고요. GRU고 이건 LSTM의 심플리파이드 버전이라고 볼 수가 있습니다. 그래서 게이트의 개수도 적고요. 두 개밖에 없고요. 훨씬 더 간단합니다. 이해하기가 좀 쉬워요. 오케이. 네. Okay. But decoding is not trivial still because training and inference are both tricky for the decoder. And there are several important tricks. Teacher forcing for training and beam search for inference. Let's see. During training, what happens to the next word prediction when the decoder's current step predictions is wrong? For example, this is the RNN training process. And now here is the start token, and the current output is 2, and 2 is used for the next time step input, and this will predict the bird, and the bird is now the input for the next time step, and flying is used. Okay, so this is the typical RNN training process, but we do not know that this is the same, this is the ground truth, okay? This is just prediction. Prediction is always, so the prediction is not necessarily to be true, okay? So if the prediction is false, then the error will propagate to the next time step. And that is really bad because we want to train our model with accurate information. But in the due to the architecture of RNN, the error can propagate. Okay, so there are two options. And the first option is simulating inference situation. We feed the prediction as the input for the next word prediction. Okay, so this is the feed previous. And there is another option. We want to make sure the input of each time step is correct. Okay, without in this feed previous situation, the input of each time step cannot be correct. Okay, may not be correct. So and the another option is we nevertheless feed the ground truth for the next word prediction, and this is the teacher forcing. So in the first start token, two is predicted. Fortunately, two is the ground truth. So two is used for the next time step, and bird is predicted, but this bird is not ground truth. And people is correct. So people is used for the next time step. This is the time. This is the teacher forcing, and this teacher forcing is usually preferred. So with some caveat. 자, 그래서 피드 프리비우스와 티셔 포싱에 대해서 이야기를 했는데요. 렌을 트레이닝 할 때 보면은 이 아웃풋을 다음 스텝의 인풋으로 사용할 수가 있는데, 그렇게 되면은 에러가 혹시 초반에 발생하면은 그 에러가 끝까지 프로퍼게이시 됩니다. 그게 이제 싫은 거죠. 그래서 티처 포싱이라는 걸 사용합니다. 뭐냐면은 각 아래 있는 스텝의 인풋은 반드시 그라운드 트루스가 입력이 됩니다. 이것을 우리가 티처 포싱이라고 하고요. 티처 포싱이 좀 더 선호됩니다. So during training decoder, we use the shifted ground truth as the input. This allows us to avoid error accumulation in the early stage of training. This, however, induces exposure bias during inference because the ground truth is never observed during inference. So what is exposure bias? That is, so during training, our network always use the ground truth information, right? But in the during inference, there is no such information. We cannot use ground truth during the inference. So our model may confuse because it cannot use the ground truth information. That is exposure bias. And the bias does not seem to be severely hurting the performance though. But for sure, it makes some unwanted behavior. Okay, so some people use reinforcement learning to avoid the bias, but it has too high barriers to work well in practice. 자, 이 티처 포싱이 그 에러 어큐뮬레이션 아까 얘기했던 그 에러가 초기에 발생했을 때 그게 계속 프로퍼게이트 된다고 했었죠. 그게 이제 그런 거를 방지하기엔 좋아요. 근데 이제 그 티처 포싱을 쓰면은 입력을 그런 트루스를 넣어주는데 이게 무슨 얘기냐면 언제나 그런 트루스가 입력이 된다는 얘기입니다. 그러니까 이게 좀 잘못 들어오는 거를 아예 배우지 못해요. 잘못 들어올 수도 있는 건데 말이죠. 그래서 그런 이제 트레이닝과 테스팅과의 간격에서 오는 그런 바이어스를 익스포저 바이어스라고 합니다. 이게 그렇게 막 성능에 큰 이제 손해를 주는 건 아닌데 주긴 줍니다. 분명히 주긴 줘요. 그래서 이것들을 줄이기 위해서 많은 방법들이 나왔는데 보통 레인포스먼트 러닝으로 이 문제를 풀려고 하는데요. 이게 잘 안 됩니다. 바이어스 줄이려다가 베리언스를 너무 크게 하기 때문에 실제로 쓰기가 너무 어렵습니다. So every bias is not. So bias is in general, bias is bad, but we always find the sweet spot between the bias and variance. And if the performance hurt is not that severe, for it's not that severe, then we just take the point, the trade-off. Okay. So there are two methods, two approaches for avoiding exposure bias. The first thing is enumerate all possible outputs and compute the gradient. But this is impossible because we cannot enumerate all possible outputs. This is really, really large. V to the t, O of V to the t, which is very large. We cannot handle this large large space, and we cannot compute the gradient for all these possible outputs. Okay, so this is impossible. So there is another way, using policy gradient, which is the reinforced learning method, and there is no bias but very high variance. So if you're interested in this second approach, consider taking reinforcement learning class. This is very different approach. So we do not cover this reinforcement learning part here in this class. And now this is the search strategies during decoding. Decoding can be considered as a search problem, finding the output with the minimum perplexity. So we did not we did not see the perplexity yet, but maybe this can be thought as error. This is not that accurate terminology, but in this context, you can understand the minimum perplexity is minimum error. Okay. Anyway, this is not the correct terminology. And why this is true? This is the case. Given the information, the decoder has to find the most appropriate result. Okay, that is finding the most appropriate result among all possible outputs, and that is actually search process. So there are three approaches for this search process. First is exhaustive search. Search through all possible combinations, which is impossible. Okay. And this is computationally infeasible. The search space is very large. We cannot compute such computations. Okay, we cannot afford it. And the greedy search. That means we choose the best word at each time step. And for all greedy search algorithm, the limitation is that it turns out the final result might be suboptimal. Okay. So to address such limitation of greedy search, beam search is used. What is a beam search? Beam search is keep top K best search results at every time step. And K is the beam size. So in this figure, this is the beam search example. These two, imagine that K is equal to 2. So we take A and C, and then take A and C, and also take two highest words, AB and AE, and here AB and AE, AED and ABC are top two results, so we take these two results. So this is the beam search. And if we use the greedy search, then only take A and AE and ABC. We cannot take, sorry. And then take AED. We cannot take ABC. So here, the result of AE, okay. So this is an example of greedy search and beam search. 자, 그래서 디코더가 하는 일은 모든 아웃풋 스페이스에서 최적의 조합을 하나 딱 찾아내는 거거든요. 그래서 이제 기본적으로 서치 알고리즘이라고 볼 수도 있는 것인데요. 이저스티브 서치는 할 수가 없습니다. 너무나 경우의 수가 많기 때문에 안 되고요. 그리드 서치는 이제 각 타임 스텝에서 최적의 결과만 고르는 것인데 언제나 그렇지만은 결과적으로는 최적이 아닐 수가 있습니다. 빔 서치는 이제 탑 K개만큼 골라서 가는 거죠. Okay. Now this is a bottleneck problem. So you cannot cram the meaning of whole sentence into a single vector. So here is a figure. Now this C includes all information of these input sequences, right? And this is somewhat nonsense, I think. And many people thought that this is not possible. Okay. For example, if we use the 128 vectors, and if we assume that we use the floating point 32 4 byte, then this vector C can 512 bytes, right? And of course, this is very, very small size. And you cannot store all the information of your text into this small vector. Okay, so this is the talk from ACL 2014. So, in order for encoder-decoder to work, C has to contain all the information in the source sentence. This means a lot of compression, which is implicitly hard. Can we directly access the source sentence? So the problem of this bottleneck this encoder-decoder architecture is that all the information have to go through this vector C, which is very small. Okay. So the motivation of addressing this limitation is access the source sentence directly. That is the basic motivation. And that is the motivation of attention. Decoder with attention. Neural machine translation by jointly learning to align and translate. So this is the first paper. I think this is the first paper. NMT terminology is used from the same institution, University of Montreal. So in the image domain, so this NLP domain, this University of Montreal is one of the first institution that introduced a very important milestone for NLP. Anyway, what is the attention? Instead of summarizing the entire input into a single vector, allow the decoder to directly access few relevant input tokens. Okay, so the keyword is that directly access few relevant input tokens. So the act of canonical memory access is non-differentiable, so we approximate it by attention mechanism for differentiability. That is, we take all these hidden states and compute the weighted sum, right? And this is the learnable attention weight. And we now the output of this, so this weighted sum is now the new summary vector C. So the attention is dynamic summarization per decoding step. So this is the attention, but very different form from the attention nowadays. Okay, recent the attention from in the transformer. So the CI. So this is the summary vector C, but now with index I. And that means this summary vector is computed for each time step and using the attention weight and the hidden state. And this attention vector can be computed by softmax of Eij. What is E? That is computed by using the previous S and current H. Okay. And this is linear transformation, I think, any function. So this A is the linear transformation actually. And the linear transformation of previous S and current H, and they are summed, and then they go to the nonlinear estimation, and then finally take inner product with a vector, because this is the vector, not a scalar. We need a scalar value, because we need to take weighted sum. So we need to convert this vector into a scalar value. So we take, this is a vector, and take inner product between these two vectors to get scalar value. And we can compute the E, and then finally compute the attention weight, and then finally we compute the CI. And this is additive attention, I think. And also there is a multiplicative potential. I think that is, I'm not sure because they do not use anymore, but I think it would be like this. This is the room. This additive attention is Paranauer. Okay. They are concurrent work. The only difference is that how to compute the attention. Okay, so a new era of NLP begins. Machine translation was very important since 1950s, and this SMT was dominant until 2015. And this SMT was extremely complex and involves lots of feature engineering. But this neural machine translation is extremely simple and fluid. NMT became comparable to SMT in 2015. Okay. Sorry, I'm not sure. It's okay. This is 2015. And outperformed with a large margin in 2016. So, in 2015, relatively few deep learning papers at NLP conferences, but by 2016, and everyone realized that this can be applied everywhere in NLP. So this is the paradigm shift in NLP. And this, for your information, this was 2013 or 14 in image domain. Our assumption is that every vector corresponding to its input token is highly contextualized via bidirectional LSTM. But this assumption may not be held if the input sequence is long. Can we do better attention than Paranauer? Can we get away with the recurrent neural net? And this will be covered in the next lecture. Okay, and that is transformer. Okay, so this is the quiz. This is a base rule of P of y given x, and does not hold true if y3 is not independent. Okay, this is false. This is always true because this is a base rule. And similar to text classification and token classification, we can often compute the exact MLE loss for text generation. Okay, first, text generation cannot be computed using MLE laws if the sequence length is larger than 1. And the encoder-decoder, the input length does not have to be equal to the output length. Okay, this is true. An attention mechanism with softmax is not differentiable. And okay, this is first, that is differentiable. And given attention weights of n vectors, this is 0.2, 0.8. Attention performs softmax on affinity scores. This is very easy, 10,1. Okay. Our lab objectives are implement teacher processing in encoder decoder and implement a simple attention mechanism in encoder decoder. Okay, this is it. Let's see the lab in the next class. Thanks for listening.